So in the last video, we explained what is the sigmoid function, when to use it, and some interesting properties of the sigmoid function, and we saw how to compute the derivative of the sigmoid function with respect to a scalar input z. So we said the gradient of the sigmoid function is equal to the sigmoid function times 1 minus the sigmoid function, and we've proven how to calculate this derivative. Now in this video, we will take it a step forward and we will compute the vectorized form of this derivative. What do I mean by the vectorized form? Well, in some cases, in the example that we gave last video, we used this example where we had a cat classifier model that took an image of a cat and it vectorized it into, it took all the pixels of the image, we vectorized it into one tall vector, and we did a linear transformation, W transpose X, we call that Z, and then we applied the sigmoid function to Z to generate a probability between 0 and 1. And then we said that the rate of change of the prediction with respect to the weights is the derivative of the sigmoid times the derivative of Z with respect to W, which is X transpose. Okay, so what if Z is not simply a scalar value like 1, minus 1, 2, 5. What if Z is a vector? Z1, Z2, Z3. When will that happen? Well, basically so far, or in our previous example, we were explaining if we have just one image, but what if we have a mini batch of images, right? So what if we are predicting or training over a set of images? So we will have a score for each different image. Or if we are doing something like a multi-class classification, so each class will have its own score. So in practice, this Z is not just one scalar, it's a vector representing each image or each class. So how will we go about computing the sigmoid of Z and the derivative of the sigmoid? Well, first of all, the sigmoid of Z, well, it turns out that sigmoid function is an element-wise function. What's an element-wise function? Element-wise function, which means that the sigmoid of function or a sigmoid of a vector applies to each element of the vector in the same way. So the sigmoid of Z is nothing but the sigmoid of Z1, the sigmoid of Z2, and the sigmoid of Z3. I'm limiting to just a batch of 3 images for simplification, but this could go all the way up to sigmoid of Zn. Okay, so the sigmoid function is an element-wise function because it applies to the elements of the vector Z1, Z2, and Z3 in an element-wise fashion. So this is how the function will look like at the end. It will be 1 over 1 plus e to the negative Z1, 1 over 1 plus e to the negative Z2, 1 over 1 plus e to the negative Z3. Okay, so how will we go about computing the partial derivative of Z, of the sigmoid with respect to Z, which is sigmoid prime of Z? Well, if you go back to our matrix calculus video, we always call this F1, F2, F3. And if you remember, now the sigmoid function is a vector valued function because it returns a vector, and Z itself is a vector. So the derivative of a vector valued function with respect to a vector is a matrix that's called a Jacobian. So what is the Jacobian of the sigmoid function? That will be partial F1 by partial Z1, partial F1 by partial Z2, partial F1 by partial Z3, partial F2 by partial Z1, partial F2 by partial Z2, partial F2 by partial Z3, and partial F3 by partial Z1, partial F3 by partial Z2, partial F3 by partial Z3. This is called the Jacobian, or the matrix of partial derivatives. This is the Jacobian of the sigmoid function, or sigmoid prime of Z. But if we try to compute the actual values for this Jacobian matrix, we will notice something that is really important. So what is the derivative of F1 with respect to Z1? This will be the the derivative of the sigmoid at z1. But what will be the derivative of f1 with respect to z2? Do you see any z2 element in this equation? No. And what is the derivative of f1 with respect to z3? Again, there is no z3 element in this equation, so there'll be 0 and 0. If we look at f2, what's the derivative of f2 with respect to z1? Again, there isn't any z1 element here, so this would be 0. Derivative of f2 with respect to z2, that will be the derivative of the sigmoid function at z2, and with respect to f2 with respect to z3 will be 0, and again 0, 0, and the derivative of the sigmoid function at z3. So this is very interesting. So the partial derivative of the sigmoid function with each element of the z vector results in a very sparse matrix, which is as a Jacobian, so a very sparse Jacobian where most of the elements are 0 except for the elements on the diagonal. Did this come by chance? No. This happened because the sigmoid function is an element-wise function, so it applies to each and every element separately. So that's why the derivative of f1 with respect to any other element except z1 will always be 0, of f2 with any other element other than z2 will always be 0, and same for f3. So the Jacobian of the sigmoid function is a sparse matrix where all the elements on the diagonals are the derivatives of the elements of z1 and z2 and z3, and all the other elements are 0. So this is interesting because we can use this fact to calculate a compressed version of the Jacobian. There is now no need to compute all of these useless elements that we know for sure will result into zeros. We can just compute the diagonal elements and that's it. So instead of computing the entire large matrix, the entire large Jacobian, which is the vectorized derivative of the sigmoid function, instead of computing this entire big Jacobian when we know that all the elements will be zeros anyways, we can just calculate the diagonal of this Jacobian matrix, right? Which is just the derivative of the sigmoid at z1, the derivative of the sigmoid at z2, and the derivative of the sigmoid at z3, and that's it, right? So this will be sigmoid of z1 times 1 minus the sigmoid of z1, sigmoid of z2 times 1 minus the sigmoid of z2, and lastly sigmoid of z3 times 1 minus the sigmoid of z3. So we have used this interesting property that sigmoid function is a element-wise function, and this enabled us to only, instead of computing a 3x3 Jacobian, we are only now computing just 3 elements. So when you have a matrix of Jacobian matrix of 1 million by 1 million attributes or derivatives, you don't need to calculate all of these elements. You need to calculate the elements on the diagonals. This only applies when you are dealing with an element-wise function like a sigmoid function or a ReLU, or usually activation functions are element-wise functions. So how can we use this to our advantage? Now, since that we have only 3 values to compute, I'm going to do so if we go back to our original slide, we will see that what we're trying to compute right now is how the output changes with respect to the weights. So let me write it down here. Partial P by partial W, how the predictions change for a change in the weights. We said that this is partial P by partial Z times partial Z by partial W. We said that this is X, and this is nothing but the vectorized derivative of the Jacobian. So let's do it first. Number one, let's do it the inefficient way. What is the inefficient way? I'm going to use the entire Jacobian. So I'm going to give some values to those diagonal elements just to show you that it's the same computation. So I'm going to assume that this matrix evaluates eventually to 1, 2, 3, and 0 otherwise. Okay. Let's use that same matrix here. So this is our Jacobian. And we will do a multiplication by our X matrix, X2, X3. So row by column, this will result into x1, 2x2, 3x3. This is the inefficient way where we had to use the entire Jacobian. What will be the efficient representation? Instead of using the entire Jacobian, I'm just going to use the diagonals of the Jacobian, 1, 2, and 3. And I will multiply that element-wise multiplication this time, not a dot product, but an element-wise multiplication with x1, x2, and x3, which is nothing but the upstream gradient, which is dz by dw. This will result into x1, 2x2, and 3x3, which is exactly the same as the result we got when we used the entire Jacobian matrix. So this is a very interesting thing to note, that when you compute the vectorized gradient of any element-wise function, sigmoid or Rayleigh or whatever, always remember that you do not need to compute all of the elements of the Jacobian. All you need to do is to calculate the elements, the derivatives on the diagonals using the equation we know. The gradient of the matrix is the gradient of the sigmoid is nothing but the sigmoid times 1 minus the sigmoid. Substitute that into to calculate only the elements and the diagonal. Do an element-wise multiplication with the upstream gradient, and you will end up with the gradient that you're looking for. That was it. Now we have seen how to calculate a vectorized implementation of any element-wise function. We've applied that on our sigmoid function. If you find this video helpful, don't forget to smash the like button on your way out. It helps a lot. Thank you so much, and I will see you in the next video.